Alex, I'm going to start, okay?
Great.
Okay, great. Hello, everyone. We are hosting a hybrid webinar today with Dr. Alex Lidow. He got his undergrad from Caltech and PhD from Stanford. He's a co-inventor of the MOSFET power MOSFET that everyone knows. It's kind of silicon power devices. And then he was the CEO of International Rectifiers Corporation with almost 10,000 employees. Later Tom, he co-founded and currently is a CEO of Efficient Power Conversion Corporation, EPC. He wrote the first handbook on gallium nitride devices, on gallium nitride transistors, that is published by John Wiley, and it's right now in the 3rd edition. He already also published lots of journal papers, conference papers, and he had a journey from academic, from undergrad, PhD, to become CEO of one of the greatest and biggest company in power electronics. He had different hats on. He's been doing different jobs in International Rectifier Corporation, and right now he's a CEO. We see him as a role model for the students that they're interested to work in hard techs in semiconductor, because he had lots of experience in career development, in technical development, and be both a technical innovator and a businessman. So we are very honored today to have him in this webinar, and the ground is yours, Alex. Please go ahead.
All right. Thanks so much, everybody. And let me just say that, it took a lot of soul searching to go back over about 50 years of personal history. But I'm going to show you stuff about myself that I hadn't even thought about for many years. So first of all, what was my journey? This kind of is, a life story here. I started off, I went to California Institute of Technology, started in 1972. And I went there because I thought it was a very difficult school and would really test my abilities. But while I was at Caltech, in looking back at it, there were 3 things that I gleaned from, I'll say, a very rigorous education. And that is, a sense of ethics. Caltech very heavily emphasized, ethical work, ethical life. Also discipline. You had to have discipline in order to even succeed, even to pass the class, you had to have discipline. And also inspiration. Many of the students and many of the professors deeply inspired me to both be a better person and a better technologist. And then I went to Stanford for graduate school. I started in 1975. And while I was at Stanford, as a graduate student, you sort of, it's less about classes, more about research. And I really developed mission number 1 and mission number 2, which I'll describe in a few moments. But my life's missions, professional missions, came out of my graduate work. It gave me time to reflect on what I really want to do as a professional for the rest of my life. And then I joined International Rectifier. I joined International Rectifier because of a few things. One was it was a vehicle for me to complete at least mission number 1. And I will describe that in a minute too. And after International Rectifier, when mission number 1 was kind of complete, I went to EPC. I founded EPC and went on to do both mission number 1 again and mission number 2. And that's where I am today. So let's go through this journey together. So when I said that mission number 1 and number 2 came from graduate school at Stanford, it really stemmed from an April day in 1976. A friend of mine who was also I guess an assistant professor at that time was talking to me. We were in the lab together. I was doing some experiment or whatever, and he took off his glasses and he said, "You know what makes these glasses cost what they cost?" And I said, well, I gave some sort of a strange answer, I guess. But he said, "No, what makes these glasses cost what they cost is all the energy it took to bring it to this state." And he went on to describe that everything that we have, everything that we buy, everything that we do is related to the cost of energy. And there's 6 elements to that cost. There's a cost of generating the energy, and that's very different if it's wind generated, solar generated. He happened to be into solar. coal generated, nuclear, whatever. They're all different means of generating the energy. Then you have to distribute it. As you can imagine, there are very big differences in distribution costs between wind energy and, say, solar energy, where it may be local. Then there's storage, and storage is a big element. If you have daylight only 8 hours a day, you have to store energy somewhere, but you don't have to if you can run a coal plant 24 hours. Then there's conversion. How do you convert this into energy? For example, an internal combustion engine is very different than an electric motor. There's consumption. How do you consume this energy? And then finally, cleanup. And cleanup is something that he said is not well incorporated into the cost of energy, and it's out of period cost. It's something that is deferred to the future. And this was 46 years ago. And as all of us who now know about climate change and global warming and all that kind of stuff, we understand that this cleanup issue is a major element in the cost of energy, and it's one that still is not incorporated in the cost of energy. And as a result, we don't make the best energy choices. So with that, I developed a mission. And that was mission number one. I wanted to improve the global standard of living by better energy efficiency. Well, if everything is related to the cost of energy, if you make it more efficient, well, you make it cheaper in effect, and therefore people can live better. And that was my first mission. And my second mission was find the successor to silicon. When I went to graduate school, I felt that, well, gosh, silicon had been around for 20 years. It's got to be obsolete by now. And I wanted to be the one that found the solution to it. Turns out that was a longer mission than I thought. So here's the journey as it began at International Rectifier. Focus on mission number one. I was given the challenge when I joined International Rectifier to make a better transistor. And I recognized that by making a better transistor, you could make more efficient power conversion. You could do all sorts of good things. It would be a big deal. I didn't know how big, but we developed the power MOSFET. My friend from graduate school and I together developed the original power MOSFETs, which maybe you've learned a little bit about over the years. But I also learned what it took to create a new culture, because I was in a company that had existed for many, many years, and it was a very calcified culture. You know, everybody was older, they were middle-aged. I was this young kid. They didn't know what this young kid was doing and why he was doing it, and they didn't like it because it was different than what they were doing. And so it really was a challenge to create a new culture. My buddy and I, we could invent something, but then what do you do with it if everybody's fighting you? The salesmen, they don't want to sell something new. The manufacturing people don't want something disrupting their factories. So we had to learn what it took to create a new culture. And once we did, we started building new factories, hiring new people in different locations all over the world. And that became the culture. Originally, when we started, there were about 30 employees, maybe 100 employees around us. When we started going, we had thousands of employees. So creating the new culture was important, and that new culture had to conform to the requirements of the mission. And that was an important thing. Many of the people that were in the older culture, they retired. Some of them had to be fired. Some of them changed and became real stalwarts of the new generation. And I'll tell you about one of those gentlemen in a minute. But that was part of this big journey of saving the energy. And then finally, I was promoted from R&D engineer to manufacturing to sales marketing, finally CEO. And for the last 12 years I was there, I was actually the CEO of the corporation. And then I got fired. I'll talk a little bit about that too, because that is part of a journey. Many of you will experience that part of the journey, and it's not a pleasant part. So how do we do this improving conversion efficiency? Well, I was given the task on day one to make a better bipolar transistor. And the head of R&D said, make a better bipolar transistor. Here's the specs for it. And it was a little bit better than the bipolar transistors that were out there. And my buddy and I said, well, maybe the issue is that it's overspecified. Maybe we just make a better switching device. And we developed a MOSFET. Later generations of MOSFETs, also a cousin of the MOSFET, is the IGBT. And that journey saved 30 to 40% of the world's energy. That's pretty well documented today. So let's examine that. I mean, that was something that came out of all the things I'd learned in my career up to that point, which was about 6 weeks out of graduate school, that we came up with this development. And how did that happen? Well, so after reflecting on it for many, many years and for many weeks since I was given this assignment, here's some of the lessons. First of all, on day one of the old school guys, his name was Bill Collins, gray hair, he's a crusty guy. He was like, he was old. As a matter of fact, he was about 20 years younger than I am today, but he was old for me. And he came in and he didn't say hi. He looked at me and he said, "What's the definition of an engineer?" Challenge each of you to come up with your own definition of an engineer, but he came up with the best one that I've lived with my entire life. Said, an engineer is somebody who can do for 50 cents what any damn fool can do for $1. Now get to work. And that was one of the most valuable lessons I've ever learned, because it's really true. Now, he also gave me a specification for a better transistor, and he recognized, by the way, not to overspecify the problem. So he took that first assignment that was given to me by the head of R&D, and he was a marketing guy. And he said, yeah, if you can do it some other way, that's fine. Just do it for 50 cents. And off we went. And my buddy and I, we developed a new type of transistor, a power MOSFET. And it worked pretty well. And everybody was pretty excited about that. But the rest of the world in the company thought that that was an inconvenience. And you will find in your careers, when you do something new in a place that's used to doing something in another way, they will come after you like antibodies after bacteria and try in every way, shape, or form to avoid the struggle that they will have to go through to change a culture. And learning how to change a culture can't be generalized. All it can be generalized is that if you know you have to change a culture, you have to examine that culture very carefully and figure out what it needs to be, and then start moving in that direction, both by incentivizing people that have those new attributes, rewarding them, and by moving out people who don't. And it's a hard reality. So what do we do to change a culture? Number one, you have to have a clear mission. You have to be able to tell people, this is what we need to accomplish. And you will see some people say, yeah, I'm not interested in that. Those are the ones that are going to be hard ones. And then you'll have some that'll cheer at the end of it, and some that'll cheer only because they know that'll save their job, and those are the ones you have to watch out for. You have to understand the current culture. If the current culture is willing to change, or if it's calcified, or if it's demoralized, or if it's cynical, or if it's overly enthusiastic to anything, those are all important things to understand, because they can all interfere in the change that you need to make. So make certain that you embody the culture that you expect. If you want people to be enthusiastic and hardworking, be enthusiastic and hardworking. That's a little simple, but it's really true. If you want to show that you value people, truly value people. Listen to them, understand what is motivating them, understand their pain, their hurt, and yet don't get dragged in so that all you're doing is taking care of other people rather than the business. So you have to embody what you want other people to do. That's an important leadership trait. If you don't want to do that, if you're not interested in that, don't get into the leadership game. Be an individual contributor or small teams. And then also find people around you that embody that desired culture. Make sure that they're the ones that get promoted. make sure that they're doing it for genuine, heartfelt reasons as opposed to sycophantic reasons, that they just want to get promoted and therefore they'll imitate what you're doing. And it's not easy always to figure that out, but it's important that you do. And you've got to be somewhat clinical, assessing people for fit or misfit. And over the years, as your successes multiply and the number of people in your culture grow, you'll find that people that fit in one stage don't necessarily fit in a later stage. And that becomes a very difficult decision. When you have somebody that you were there at the founding of whatever you were doing, and then 10 years later you find out that they now are not a contributor, but actually a detriment, you've got to make a move. And I have to say that in my entire career, and this is a hard thing to say, I've had to fire hundreds and hundreds of people. Very few of them resented it afterwards. In other words, I did it in a way that they actually respected it. And in no case that I can remember did I do it soon enough. So if you realize that somebody is a misfit, move. It's not to their advantage and it's not to yours to wait. And also be consistent. If you reward sycophants because they kiss your ass, it's going to be a culture built around that. If you reward people because they truly embody the culture and advance the mission, those are two different things. But if they come together, reward those people and make sure that you give them the skills to succeed wherever they go. So that was maybe through about day 2000, the first several years while I was there. How about the next 20 some odd years? How do you grow and stay on top? And culture change is needed for every order of magnitude change in population, from 10 to 100, 100 to 1,000, 1,000 to 10,000. Each one is a major culture change. Get ready for it, realize what needs to be changed, and make sure you have enough people to affect the change. It's very different when you're changing from from yourself to 10 people, where you can talk to everybody every day, to where you have 10,000 people spread out over 22 countries, where you can't. So you need to have missionaries, and you need to travel a lot and visit the people and really care a lot about them. Back even 20 years ago, there wasn't Zoom, there wasn't WebEx, none of these things were there. But I would say that relying on those too much is another very, very bad trap, that you need to be with people. And that is where the big impact occurs. Secondly, frequent, precise, and consistent communications. And as you get bigger, the need for this escalates. It takes more and more of your time. You have to, and by the way, this is one thing that's been made a little easier. Every 2 weeks, I communicate with everybody in the company in various company meetings. I can do that every 2 weeks, even though they're spread out around several countries. It doesn't take the place of face-to-face, but it certainly helps. So here's where technology has enabled something, but make sure it's concise, it's precise, and it's consistent. If every week you're changing priorities, if every week you're complaining about a different thing, people will just get muddled. They won't understand what's needed. Internal professional growth is important, and as you get bigger, it becomes even more important. Corporations that don't provide for internal professional growth see high turnover. People will see that their career is enhanced better by changing jobs than by staying at a job and getting promoted. And so it is important to have not just career ladders, but professional growth. Not everybody wants to be a boss, but they want professional growth. They want, because it's more interesting, frankly. It makes it interesting for a lifetime. So make sure you incorporate that into your thinking in an organization. It's one of my big lessons there. Okay, and then beware of becoming too insular. This is certainly that occurs with bosses. They stay in their office. They surround themselves with a small group of advisors, and they don't know what's going on. There is an inclination to be that. It is easier. You are encouraged by your people around you to do that. Don't fall for it. Get out there, meet the people, talk to them, learn what they care about, and be visible in person. So what about these last few days getting fired? So I learned a lot of things. It was a publicly traded company, New York Stock Exchange. I was on top of the world. I, personally developed many of the products that were there. And by the way, well respected by the folks in the company. I had a board of directors. Board of directors are people that come in and every 3 or 4 months they come in there. They're supposed to make sure that governance is good, that nothing is going astray. For those of you who are Disney fans, it's like Jiminy Cricket sitting on your shoulder. They should be whispering in your ear. Don't do that. Boards can develop strange attributes, especially since they're usually long-term. In other words, people stay on those boards for many years. I happen to have a board that had management consultants, a couple of them. And a lesson learned, don't ever have a board with management consultants on. They felt that they knew how to run a business, but had never run one themselves. You get a few of them together and they start figuring out how to run your business. And then when you don't agree with them, they figure out how to get rid of you. And that's what happened. And board politics have nothing to do with the real business at hand. They booted me out. And it was a very traumatic thing personally. It was traumatic for many people because they had to fire the whole cultural thing. They had to tear out a bunch of people that wanted to do it, if you will, my way, to do it their way. And they brought in a bunch of consultants. And the company eventually, very quickly, actually started falling down and got sold. Got sold out because they didn't know what to do with it. So it was a very sad thing. I also learned that there are very few true friends. You will learn that in your life. It's a hard lesson. But most people will tend to, protect themselves as well they should, protect their job over what they think is right. And then there are a few that will actually do what's right. And those are valuable people. They're valuable from a human point of view, and they're also valuable from a professional point of view, because several of those people left the company on their own and came to join EPC and have made EPC a success as a result of it. So I was fired, and pretty abruptly. I would say surprisingly. I didn't think it would happen, and it did. And one day I was sitting in the shower, and I was told that day there was going to be a board meeting, and I was going to be fired. Standing in the shower. What am I going to do now? What am I going to do now? I was in my mid-50s, by the way, so it's kind of hard to think about starting over in your mid-50s. I had no golden parachute. I had nothing. No, none of that. So it was what I came in with, and I thought, well, what do I want to do? And I thought, I got an idea. I'm going to do carbon futures because that takes care of that cost of energy. And then I thought, but another minute, before the water started getting cold, I thought, I don't know anything about carbon futures. Maybe I'll do gallium nitride. And the reason is that gallium nitride was that second mission. I had learned that there was a way to grow gallium nitride on a single crystal of silicon that could make devices better than silicon devices. And that might be the answer to obsoleting silicon. So we started with this mission. A few of my colleagues from my former job, they took a risk and left their job to join me. And we said, let's make power conversion devices that are higher performance and lower cost compared with silicon. That is the formula for obsolescence. If you make something higher performance but higher cost, you get a niche. If you make something lower performance and lower cost, you get a niche. If you make some higher performance and lower cost, eventually you own the whole thing. So let's do that. Replace silicon. And that's mission number 1 and mission number 2, because if you can do that, you can save energy as well. So now, finally, I'm on mission number 2. I'm in my mid-50s. Why gallium nitride? Well, compared with silicon, GaN is smaller. Devices can be smaller. They can be faster, which means more efficient. They can be lower cost. They can be radiation hard. I had a very booming business at International Rectifier in satellite electronics. More reliable than silicon. That compound semiconductor is a stronger chemical bond, makes it more reliable. Not only that, but you can integrate these things in gallium nitride much easier than you can in silicon. That was a big deal. So we did that. That was 15 years ago. Today we have a booming business in gallium nitride. I think that it is generally accepted that this will replace a large fraction of the silicon power MOSFET under 600 or 650 volts. I am proud to have been one of the pioneers in that area. Where's it going today? Well, the very first application, which was really, thank goodness for that, because that really got us going, was LiDAR, light detection and ranging. And what happened was we introduced our devices in March of 2010, and in June of 2010, I got a visit from a gentleman by the name of Dave Hall. And Dave Hall is the inventor of the modern LiDAR system. I didn't know who he was, but he was a quirky guy, brilliant. And he says, thank goodness you came along, pointing to me. He says, because GaN is what I need, and I need it to make my LiDAR better than radar. And in fact, because with GaN's speed and high current handling capability, you could blast more photons out of a laser than anything else, 100 times faster than silicon. That meant you could see farther, you could see faster, and you could see better. And here's one of my marketing lessons: that pick 3 things. If you have more than 3 things that you're pushing in your product, nobody's going to remember it. So see farther, faster, and better with GaN. It is true. GaN dominates the world of LiDAR today. Autonomous vehicles, robots, even vacuum cleaners and drones have LiDAR systems on them today, and more is coming. And that got us from making a few samples to making millions of units. Then along came DC to DC. Next lesson learned: if you have a better device, but nobody has an open design window, you will get nowhere. We looked at where are the big changes in the world, and one of them was that people are going to higher voltages for conducting current in things like servers, AI machines, gaming machines, and cars. And that meant there were hundreds and hundreds of design windows opening for something that could efficiently convert from 48 volts to something, or from something to 48 volts. And we designed a ton of products to absolutely focus on that node. And we designed them to be cheaper than silicon, more efficient than silicon, smaller than silicon, and they are more efficient, smaller, and cheaper. 3 things. And in fact, we have a booming business there. Motor drives. I love motor drives because there are an awful lot of them, and they are just about everywhere. So we designed, but we realized that in order to get into motor drives, there are new things that we had to do. So we designed integrated circuits that did almost all the function of a modern brushless DC motor drive. And by doing that, we were able to make things smaller, lighter, which is important if you're driving around on an e-bike or scooter or flying in a drone, and higher precision. If you've ever, and hopefully you don't, had surgery, microsurgery using robots, today's robots all use our GaN because it's able to precisely make cuts and incisions and tie sutures far better with GaN than anything else. So motors is a good thing. And then space. What's the importance in space? Smaller, lighter weight, and reliable. If you throw a satellite up in space that costs $1 billion, you want it to last 20, 30 years. So it's got to be very reliable. You don't want to take any chances because it's very expensive getting there. But smaller and lighter, of course, means that you save a ton of money. It costs about $15,000 to send a kilo into low Earth orbit, about twice that amount to get it into geosynchronous. So if you can save even a few grams, you save a lot of money, and people are really willing to pay for that. So, improving conversion efficiency, mission number one, bipolar to MOSFET, international rectifier, 30 to 40% of the world's energy saved. GaN, silicon carbide, which is something I don't do, but the GaN part of it, another 8%. I'm still on that mission, but I'm obsoleting silicon, so I got mission number two. But where are the choke points? And I point this out because this is where you all can come in. This is where you can make an impact. If you want to pick a career spot to put yourself on a choke point. Don't look at where everybody went last year, like computer science or whatever it is. Look at where the choke points are today for the big changes. And here's some of them. Better magnetics. Magnetics are definitely a choke point in power conversion, both in motors and DC to DC converters and just about everywhere. Magnetics today have all sorts of effects that prevent you from going to higher frequencies. Higher frequencies make things smaller, more efficient, stuff like that. So magnetics, big area. Lots to be done there. Lots of innovation ahead. Ecosystems. Whenever there's a new technology, whether it be an electric car or a GaN device, there is an ecosystem. Think about charging networks for electric vehicles. With GaN, there's all sorts of ecosystems. Figure out what that ecosystem is, because it's a choke point, and get into that. In our case, it's high-speed controllers. Knowledgeable engineers. Whenever you have a new technology, there are new skills. And with gallium nitride, those skills are high. Gallium nitride requires a lot more disciplined design skill than its predecessor. So somebody that's been out in the industry for 20, 30 years, they frankly have forgotten a lot of the skills that they learned in school and design, I'll say sloppy designs, because that's all that's needed, and that's okay. The minute you get with GaN, with its very, very high speed and small size, you have to be much better at things like thermal management, layout, understanding parasitic elements, EMI, things like that. So knowledgeable engineers, big choke point. When you guys are out there, if you're out there in a new field like gallium nitride, you will be very valuable. So some final thoughts. Get ahead of the state of the art while in school. Don't chase yesterday's problems. And I see that all the time. I see people just flocking to the thing that shows up as the highest salary out of college or whatever it is. And that usually is the thing that will be obsolete or make you obsolete the soonest. Decide on a mission that will stimulate your interest, but most of all your passions. And realize those are different things, because interests could be, waning after a few years. Oh, I'm bored with that. But be passionate about something, and that means a bigger goal, a life goal, like improving the world standard of living, as opposed to I like to make better semiconductors. I like to do both, and that's when you have that marriage, you can have a career that lasts a long time. Grow continuously. In some cases, in my case, being fired was one of the greatest growth opportunities I'd ever had. But I have maintained over all these years, a fanatical interest in the technologies and in the disciplines associated with it, and making companies and business and things like that. I've been able to grow continuously because I was passionate. So if you've got the interest, you got the passion, you will find ways to grow continuously. And if you are working in a place that doesn't let you do that, move. And stick with your mission. People that one day they're doing this, another day they're doing that, and then they get a higher salary over here doing this and that. You're gonna wind up, probably getting bored after a while of doing all these things. Maybe not, but if you stick with a mission, you will become the missionary that can find new ways of putting that mission forward ahead of everybody else. My mission was, first mission was energy conservation, and I think that I've been a pioneer that has moved it ahead and continues to move it ahead after almost 50 years. My next mission was replacing silicon. I had a late start in that, but I've got a good start in that. But those missions are are a lifetime mission, and I'm very proud of both of them. And I encourage you all to find similar missions. That's my message. I'm open to your thoughts, criticisms, and questions.
Okay, great. Thank you, Alex, for your question. If anyone from audience in university has a question, they can ask or they can put the question in Q&A. I received a few questions and I had also a few questions. One of the things that you mentioned from your excellent journey was changing the culture inside your company. So I have been graduated, I went to industry. I think other students also were thinking of that. When you go to a new company that already has established culture, it's very hard to change it. I think one option for you that time was to move on, possibly go to another company, find another job, just make your life easier and just find another opportunity that you can do whatever you want or you think is good. Why you decided to stay and change the culture? Because it was the hardest decision that time.
Well, I would say because I think I had an idea what I needed to do. Now, to give you an example, for those of you who've ever seen semiconductor facilities, you'll know they're fanatically clean, right? Clean rooms with spacesuits and all that stuff. Well, 45 years ago wasn't far from that. I mean, the clean rooms were clean rooms, but the company that I went to did not have experience with clean rooms. And I remember that one of my first problems was when I needed maintenance people to come in and help hook up equipment. I had to explain why they couldn't bring lit cigars into the clean room. That's the culture. Now you ask why I stay with that. Well, because I think I could clearly communicate both with my own actions and in some cases with more severe actions that wasn't acceptable. That we had to take a new standard. And the reason was, and then you have to explain the reason. You can't just say, don't do that. You have to give the why with the what. I got people that were excited by that. Oh my gosh, I was just told the what before. Now you tell me the why. I'm happy to do that. The guy with the cigar wasn't so happy, and he wound up leaving the company. But most people were pretty happy about the new result because it was change. It was more exciting. There was more things going on.
So it means like whenever you start changing the culture, there is some resistance, but at the same time, you find someone interested that is going to work on the culture. Yeah, just help you just implement it.
Especially if you're enthusiastic and have a passion, people are attracted to that. They want that. And the culture will start changing, but don't relax. Don't become insular. You got to keep doing it.
But something interesting in your career path is you have been engaged in innovation, R&D, making semiconductor devices, and then later time you moved to the sales team, sales and marketing, and later time you became a CEO. So became a CEO, I think you have been chosen to be CEO, but how you decided to just go in different jobs? Like what was your mindset that time? It was a time to move, or like it's 2 years, 3 years, 10 years in this job, so I have to get new experiences, or I need something to complement whatever I have? What was the mindset for these moves?
Well, they weren't actually moves. I basically took over more and more areas. So I maintained the R&D responsibility for 30 years. I added to that manufacturing responsibility, I added to that marketing, and then I added to that sales. So each of those, every time I added that added responsibility, I had to learn about those fields, and that was a big challenge. But I didn't switch from one to the other. It was more of a, creating the whole cloth of an enterprise.
Just something here is, you talked about being fired as a CEO of Infineon, and then later time starting Infineon bought the company, of course. But you later time decided to move on and make gallium nitride. So you decided to stay original, or keep your mind original or passionate, as you said. Here is at the same time you mentioned in your slides that you were trying to kind of analyze the performance and people behavior, of course. and find the fit and misfit to the culture that you had in your company. Just from an employee point of kind of view, if they wanted to stay or keep the job, they possibly showed some flexibility, but they were not original. But some of them, if it's something original that they good thought, they stayed original and they lost the job. So
I don't know what you mean by stay original. I mean, I think that there was plenty of room to be original within the framework of a culture. A culture, has attributes like creativity and originality in it too, and those were important attributes, by the way, of a culture. So if the culture is confining, then people will have to leave. If it's Big Tent, then you get lots of different people in it.
That makes sense. That makes sense. Some interesting point from like founding EPCs, as you mentioned, you decided to work on gallium nitride. So you're thinking, what's the next kind of journey for me? Like you have been, of course, a CEO of a company. You had a view of the market. You have some insight about what's happening, and you were looking for some niche of kind of technology. And then you start to develop gallium nitride, and then go after customers that the markets they are there. And as you mentioned, later time make an ecosystem with other partners. But like for new students that they're working in new technology that is not already, they don't have too much experience as you. Do you think, is it a different path? They have to first develop the technology and go after the market, or the same path as you, they get some advice and they go after the market, they freeze a market, or they have some agreement and then they start the technology development? How do you see that?
I think that there are many technologies that were developed in search of a problem. And some of them found the problem and became great successes. Facebook would be one example there. But I think that it's better if you have a sense of what problem you're trying to solve. In my case, it was clear. I was trying to make energy more efficient, and I knew where the choke points were in that. In those days, bipolar transistors made very inefficient power converters. So I knew if I could do that better, I can make an impact. And then that led to another thing and another thing. So I suggest understanding your greater mission before developing a technology. It's not always the case that works, but I think it's the most reliable way.
Okay, great. We have a question inside of the classroom in Waterloo. Pranav, do you want to go ahead?
Yeah, there's a speaker up here. Okay. Yeah, so I had a question about how did you, first of all, nice to meet you. I'm in a small startup. But I just wanted to ask about how you were able to determine gallium nitride was the answer to your problem instead of silicon carbide or diamond or some other material. And also what made you confident in the technology maturity level or to pursue that path? And
so that's a fabulous question. When I was in graduate school at Stanford, I was working on gallium arsenide because I thought that was the material of the future. I got my PhD working in gallium arsenide, but by the time I got my PhD, I knew it was not the material of the future for a few reasons. One is it was fundamentally expensive because growing the crystal required a higher energy of formation than growing a silicon crystal. What that meant is it's fundamentally expensive crystal, and therefore you have a problem with competing. Secondly, it was very delicate. If you took it above 330 degrees centigrade, it sublimed, and what it sublimes is arsenic. So I knew that was bad. And then third, it was very difficult to do all sorts of things with it because you had to stay at lower temperatures. And as a compound semiconductor, it had more weird vacancy effects and things like that. So I by the time I graduated, I said, oh boy, silicon's pretty good. And I went to silicon. But I kept in the back of my head what the problems were with gallium arsenide. And in 1999, a group of researchers in Japan grew device-grade gallium nitride on top of silicon, a standard piece of silicon. And that set the light bulb off because I knew, number one, gallium nitride had a higher energy of formation than silicon, but if all you need is a very thin layer, a micron or so, that cost is insignificant. So that took care of that one big problem. Secondly, gallium nitride has a much, much higher temperature at which it starts decomposing, about the same as silicon. So I said, wow, that means I can make it in the same equipment as silicon. So I now could recycle silicon factories or utilize silicon factories to make gallium nitride. Not only that, but it had some properties that were much better than silicon. A tighter bond meant wider band gap, which meant you had a higher critical electric field, which means you could bring terminals closer together. It also had a quantum mechanical effect called a two-dimensional electron gas. I'd seen that in the 90s from various researchers. So all those pieces fit together, and I said, wow, this solves all the problems. And with that confidence, I formed EPC, and slowly but surely have convinced others of that.
Cool, cool. Thank you for that answer. Can I ask, sorry, another question?
Of course.
So like how, yeah, so to like understand that, you're saying like basically it solved all the fundamental problems. But in terms of like execution then, the Japanese group first did it. How were you able to kind of bring that like epitaxy technology to you? Like, did you buy their patent? How did you like bring that ability in-house, or like did you redevelop a new way of doing it, or just?
So yeah, how you do those things. Sometime out of desperation, you find wonderful ways. When I was fired, and as I said, I was fired very abruptly, no golden parachute or anything. So I had no money, no money to speak of at that point that I could use to fund some big startup. So I went to several people and said, hey, can I use your wafer fab to make some experimental wafers using gallium nitride? And most people said, hell no. And then one of the people I'd worked with before, who owned a factory in Taiwan, said, yeah, I'll try that. And because of that, we were able to actually not only try it, but he financed the company. And to this day, he and I together have put all the money into this company. So I was very, very fortunate to have a colleague from my past. As I said, true friends are rare. And he knew that that the firing from International Rectifier was a silly thing on the part of the board of directors, and he wanted to be in business with me. So through reputation, I was able to open more doors, if you will, to ways of getting financing.
Oh, thank you so much.
We have a question from C. C, you want to ask? You can talk. C Wang.
Cool.
Yeah, let me just. Yeah, thank you, Alex. I'm C. I just want to ask some a quick question. So, what is the most difference of doing research between industrial and academia, and what's the most challenging part to develop your personal career when you're doing research in industry? Thank you.
Well, first of all, I think that fundamentally all research is the same. It's about, curiosity and trying to solve problems that haven't been solved before. In academia, there's less of a commercial pressure. In some schools, more basic research, so there's much less commercial pressure. In some schools, they're aiming more towards, getting contracts from industry, in which case there is some commercial pressure, but it's very different. If your PhD takes 4.5 years instead of 4 years, or 5.5 instead of 4 years, okay, that's a consequence to you, but it's not the end of the world. If you develop a technology in industry and you're 1.5 years late, sometimes you miss the window and it's just done. So you have different pressures, time pressure being one. I think there's cost pressure in industrial research, that you have to do it, for 50 cents, what any idiot can do for $1. And so those are facets. But if you look at them as problems that have to be solved, it becomes the same as anything. How do you just problem solve through this thing? And if you enjoy the problem solving, you'll get through industrial research or academic research, and you'll be successful in either way.
Yep, I agree. Thank you.
Thanks.
Another question from inside of the classroom in Waterloo. Is that true?
Yep, go ahead.
Hi, my name is David Lau. I'm a staff member here at UW, and thanks for sharing from your experience. Just a question, do you think about retirement, or how do you kind of approach that question? You know, how do you think about that? Do you even think about it at all?
So, I mean, I'll give you a flip answer, and that is that my father retired at the age of 100, my grandfather at the age of 96, and they both died two weeks after they retired. So the flip answer is I'm working to stay alive. But the unflip answer is, you know, as you get older, sometimes you're not as useful in the same way. And some people try to hang on too long. So I think that you have to understand where your age is an advantage and where it's a disadvantage. You know, today at age 68, I think that I have lots of lessons learned. The disadvantage of that is those lessons learned can become 100 reasons why not to do something. And that is, you know, as you accumulate more and more lessons, you kind of think back that they are all good lessons, and some of them aren't. Some of them you actually misinterpreted doing something as being the reason for a success. By the way, there's a marvelous book on this subject. If any of you want it, I think it's out of print, but it's marvelous, worth getting. It's called The Mythical Man Month by Fred Brooks. And he actually developed the OS 360 for IBM in the 50s. But he talks about this philosophically, and it's really good. You have to understand how you personally evolve, how a project evolves, how an organization evolves. And if you can get that self-awareness and situational awareness, you can change what you do. Instead of being an individual contributor, even if you're a brilliant problem solver, you've got to somehow figure out how to delegate problem solving to larger and larger groups, and not being so tempted to go in there and solve it for them when they're struggling. So there's lots of those lessons that allow you to extend your career instead of becoming a barrier to success. You can become a facilitator. I know that you know, quite a few years ago at International Rectifier, I felt it was incumbent to train the next generation of power engineers. We started a very extensive training program of those engineers. And to this day, I find their rotation engineers, I find them all over the world in all the key spots in semiconductor companies all over the world. And it was because we let them make mistakes, and we let them, you know, go forward and learn during 2-year training programs and stuff. I had to let go to do that.
Well, yeah, I've heard that title before, Mythical Man Month, so I'll have to look it up again. I've never read it, so thanks for that.
It's a short book.
Okay, great. Since
I think we have another question here.
let me ask this one, Pranav, first, because it's
Sure.
related to previous comment that you mentioned about finding the problems, and then go after problems, solve the problems, be a problem solver, and then try to scale your skills, like control yourself kind of things. So just something, because we have audiences from material science, electrical engineering right now, maybe from physics. So can you share a few problems that you're looking to be solved? Like if someone comes from Waterloo says, I can solve this problem for you, like it's in packaging area, if it's material science, if someone says, I have a non-polar gallium nitride on silicon for you, or I have something that may cool your devices down 20 degrees, anything in your mind that right now you're think like it's a big barrier for me, and I'm eagerly looking for the solution. Just some hints for a student.
Yeah, so most people are familiar with Moore's Law, right?
Moore's
You know, double the transistor every few years and all that kind of stuff. In power semiconductors, Moore's Law is very different than it is in digital electronics. In gallium nitride, it's very different than in anything else. In gallium nitride, the electrical properties are determined by strain and traps. So if you want to improve the performance of a device, you have to understand strain and traps better than anything else. And today, the size of our device is 300 times larger than it needs to be at the theoretical limits of gallium nitride. 300. So the problem that we're working on is our Moore's law, and that is harnessing an understanding of strain and traps. And we do it both through, I don't do it, but we have a brilliant group of folks, most of them have PhDs, that do, for example, modeling of strain and traps, experimentation, making test masks and experiments that are insightful in improving our understanding of strain and traps, and then people that actually take that information and they can make it into a product. And those are the challenges that we face. If I can make my devices 300 times smaller, that's about 800 times lower cost. And everybody's going to want them because it's also about 1,000 times higher performance at 300 times smaller. So that's the problem I'm trying to solve all the time.
So scaling, I can say, and
Scaling.
implementing Moore's law in power semiconductor like gallium nitride.
But scaling in a way that is insightful to our materials.
Scaling,
Making a finer line width isn't going to do us any good.
like scaling toward gallium nitride, like
Yeah.
considering intrinsic gallium nitride property, as you mentioned strain and traps.
But I'll give you a challenge. If you go to any other gallium nitride producer and ask them about that, they won't tell you that scaling is dependent on traps and strain, because it's something that it requires a pretty deep insight.
So that's the truth. We have another question from Uwaterloo inside of the class.
Go ahead.
Hi, sir. Thank you very much for sharing your personal journey. I think it's very important to have this kind of session around students to get their own missions set up to overcome problems in the future when they have their own career kind of thing. It's very interesting thing. I have some few questions while I was listening to your presentation. I was wondering, you decided 2 missions. I don't know what motivated you to get those 2 missions. They are very powerful mission statements, I considered. And the second one is you are working for a very nice goal-oriented mission, very for overall improving the world kind of thing, and you got fired. And I was wondering who will fire that kind of person. I was wondering. And the third question I have is, the silicon is the dominant element now in semiconducting devices here. Do you think gallium nitride will replace in the future? Those are the 3 questions pondering in my mind.
So, on the first question, how do you get those missions? Well, I think that's the strength of an academic environment is, I wasn't in, this friend of mine that talked to me about the cost of energy, he was in a different field. He was doing something completely different than I was. So, but what he said was profound. And, in academia, there's some profound thoughts that go on. And you can really get inspired by it, as I was. And it can drive the rest of your life. So what I'd say is, be a seeker while you're in school. Find those elements that not just sound like they have, that they're interesting or intriguing, but they have major social significance. And it will click in your brain if it's a good one. So that's number one. Now, why did they fire me? Well, you'll have to ask them, but I would advise you, if you surround yourself with people who are professional consultants like McKinsey or Boston Consulting Group, you will find a lot of people that think they know how to do things and they've never done it themselves. And sometimes they want to have a hand in it and they will force it. And that's what happened. And it was a bad thing for everybody. It hurt a lot of people too. Let's see. Third question was, see how my memory gets shorter as I get older. What was that third question?
Replacing silicon with gallium nitride.
Oh yeah, what's after gallium nitride? I don't know. I think I'm probably, with silicon, it lasted 60, 70 years. I think gallium nitride and silicon carbide have probably a 30 to 40 year life ahead of them. And we've seen many things like gallium oxide, aluminum nitride, and crystal diamonds that are possibilities. They were all called out as possibilities when I was a graduate student 50 years ago. So they still are possibilities. And maybe technology will catch up with it. But I think it's 30 years out probably.
Thank you so much. I think there is more question to ask. Actually, I got question in Q&A. I have more questions to ask, but unfortunately, I think we are over time right now. Even we took too much time from you. I have to appreciate your time. Actually, it was very fruitful. I think for me, for audience, we really enjoyed it. Truly, it was amazing. Thank you so much. And if there is any final note that you want to say to the student, to audience.
I thank you for your time, and I just hope that you all can find something that is passionate and has positive social impact, and it will drive you for a lifetime. It will haunt you for a lifetime, but in a good way. So thanks very much, everybody.
Thank you so much, everyone. Thank you so much, Alex, for your time. We really appreciate it, and have a great day. Bye for now.